Tonight, we're going to explore one of the most unsettling engineering problems humanity has ever run into. The nearest star system is 4.37 light-years away, 25 trillion miles. And we know how to get there. The design exists. You build an array of lasers on the ground. You build a mirror 4 meters across that weighs about as much as a paperclip. You fire 100 gigawatts at it for a few minutes, and it leaves at 1/5 the speed of light. 20 years later, it arrives. Every number in that paragraph has been checked by people who do this for a living. Then somebody ran the arithmetic on a single speck of dust. Nothing in the design survived it. And by the end of tonight, you're going to understand why the acceleration turned out to be the easy part, and why the thing standing between us and the nearest star is a grain of dust 100 times thinner than a human hair. If you love this kind of thing, the big open questions, the ones where the honest answer is still missing, take a moment to subscribe and leave a like before we go any further. It really does help this channel find the other people who lie awake thinking about this. And tell me in the comments where you're listening from and what time it is where you are. It's a small thing, but I like knowing how wide this room gets at night. Somewhere on this planet, the sun is coming through a window right now, lighting up the dust turning slowly in someone's room. That's exactly where tonight's story begins. Now, let's begin. Let's start with something you've seen 1,000 times and never once thought about. A room in the afternoon, curtains half drawn, a single shaft of sunlight coming in at an angle. And inside that shaft, thousands of small, bright points, turning over, drifting sideways, going nowhere in particular. Household dust. You've watched it. Everyone has. Most of it isn't exotic. Skin, fibers of clothing and carpet, soil tracked in on shoes, pollen, paper. The particles run from about 1 micron up to 100, which means the ones you can actually see are the big ones. And you aren't really seeing the dust at all. You're seeing sunlight bouncing off it. Move your head and half of them vanish. The specks are harmless. Hold on to that tonight. They land on a desk. They settle along the top of a bookshelf. You wipe them away with a cloth and think nothing about it, because there's nothing to think about. Dust is the most ordinary matter in your life. Now take the same material and put it back where it came from. Between the stars, there's dust too. Not skin and carpet fiber, but the same idea. Small solid grains floating in a very large volume of nothing much. Rock and soot. The sizes are smaller than what you see in a sunbeam, much smaller. The standard models put most of the mass below 1/4 of a micron, and they fall off sharply above that. A human hair is about 70 microns across, so a typical interstellar grain is a few hundred times thinner than one hair. There is no version of it you could ever see with your eyes. There also isn't much of it. Dust makes up around 1% of interstellar matter by mass. The other 99% is gas, and the gas is almost entirely hydrogen and helium, individual atoms drifting alone. Hold that ratio in mind. We'll come back to it, and when we do, it won't be comforting. And the emptiness out there is difficult to convey, so let's put a real number on it. The local interstellar medium carries something like 0.03 of a billionth of a gram of dust in every cubic meter. That's a number the mouth can't hold, so here's what it means. Take a cubic mile of interstellar space, all of it. A block of vacuum 1 mile on every side, top to bottom. Inside it, there are about 100 grains. Not 100 grams, 100 grains. Try it from the other direction and it gets worse. Suppose we wanted to collect 1 gram of interstellar dust. 1 paperclip's worth. To gather that much, we'd have to sweep every solid grain out of a ball of space bigger than the moon. That's the harvest. Filter a volume the size of a small world and we come away with something you could balance on a fingertip. That's the medium. That's the enemy. It's cleaner than any vacuum chamber ever built on Earth. It's cleaner than the inside of a semiconductor factory by an enormous margin. If you could stand out there, and if you could survive the standing, you'd never know the dust existed. You could walk through it for a lifetime and never touch a single grain hard enough to notice. So there's nothing here, nothing at all. A few grains of rock and soot in a volume the size of a mountain. And then we change one number. Every part of what we just described stays exactly the same. The grains don't get bigger, there aren't more of them. The chemistry doesn't change, the mass doesn't change, the density doesn't change. The only thing that changes is how fast we go through it. And somewhere on the way up that scale, the most ordinary matter in the universe turns into the thing that ends the mission. Now, let's talk about how fast we were planning to go and why. The date is April 12, 2016. The place is an observation deck on the top floor of a tower in New York. Yuri Milner walks out in front of a room full of reporters, and sitting beside him is Stephen Hawking. They announce $100 million and a destination. The destination is Alpha Centauri, 4.37 light-years, and the plan is to get something there in about 20 years. Not a generation ship, not a fusion rocket. The plan works because it throws away almost everything a spacecraft normally carries. No fuel, no engine, no structure worth speaking of. What's left is a chip and a mirror. The mirror is the sail, about 4 meters across, which is a little over 13 feet, roughly the size of a bedspread. And it's thin in a way that's hard to picture, a few hundred atoms thick, somewhere around 1,000th the thickness of a human hair. Thin enough that the whole thing, if you could hold it, would feel like nothing in your hands. The chip rides behind it. Camera, navigation, a small laser for talking home. Together, sail and chip, the entire spacecraft weighs 1 gram. The engine stays on Earth. It's an array of lasers, thousands of them, phased together so they act as one beam, scaling up toward 100 gigawatts of power. That beam never touches anything except the sail. Here's how the launch goes. A conventional rocket carries the craft up and releases it a few tens of thousands of miles out. The array comes on. For about 10 minutes, the sail sits in that beam, taking tens of thousands of times the pull of Earth's gravity. In those 10 minutes, it covers something like 10 times the distance from here to the moon, roughly 2.5 million miles. Then the beam shuts off, and the craft is done accelerating forever. It's now moving at 1/5 of the speed of light. Let's turn that into something you can hold. 1/5 of light speed is about 134 million miles an hour. Divided down, and it's roughly 37,000 miles every second. New York to Los Angeles takes about 1/10 of a second. The Earth, corner to corner, takes under 1/4 of a second. If you blinked at the moment it passed the moon, it would be gone before your eye reopened. For comparison, the fastest object human beings have ever built is the Parker Solar Probe. On December 24, 2024, it swung within 3.8 million miles of the Sun's surface. It hit 430,000 miles an hour, fastest thing we've ever made by a wide margin and a triumph of engineering. It's about 300 times too slow. And that's the whole reason the design looks the way it does. 25 trillion miles is not a distance we cross with anything conventional. A chemical rocket would need tens of thousands of years. We've launched 5 spacecraft that are now leaving the solar system, starting in the 1970s. In half a century of flying, they've covered less than 1/10 of 1% of the way to the nearest star. Not 1%, 1/10 of 1% after 50 years. So we give up on carrying the energy and leave it at home. We make the spacecraft small enough that a beam can push it. Then we make thousands of them because they are cheap, and we send them one after another, and we accept that most of them fail. And it isn't one spacecraft. There's a second half to the idea, and that half is what makes it sound reasonable. Once we are building chips in quantity, each one costs roughly what a phone costs. So we don't send one, we send hundreds or thousands, released one after another, days or weeks apart, all riding the same array. Most of them will fail. The plan assumes it from the beginning. We aren't protecting a spacecraft, we're protecting a statistic. And the mission works if enough of the fleet gets through to send something home. That deserves its due before we start taking it apart, because it's a good answer to a hard problem. When we can't afford armor, we buy survival with numbers instead. Send a great many small, cheap things and accept the losses. Living things settled on that strategy a very long time ago. As for where it's going, Alpha Centauri isn't a star, it's 3. 2 of them are sun-like and circle each other closely, and the third, Proxima, is a small dim red dwarf drifting further out. Proxima is the closest star to us of the three, and the closest to us of any star anywhere. And in 2016, a few months before that announcement in New York, a planet was confirmed in orbit around it, roughly the size of Earth, in the range of distances where liquid water can exist. So there's a specific thing to point a camera at when we get there. That matters more than it sounds like it should. It's the difference between a mission and a gesture. That's the plan, and it holds together. The lasers are hard, but not impossible. The sail materials are hard, but people are building them in laboratories right now. The economics are brutal, and the politics are worse, and neither of those is a physics problem. Every single one of those numbers assumes the space in between is empty. Let's stay on that 1 gram for a moment, because it isn't a design choice. The gram is the whole architecture, and it decides everything that follows. The reason is simple. The power we need out of the laser array scales with the mass we're pushing. Double the spacecraft and you roughly double the beam. 10 grams instead of 1, and the 100 gigawatts becomes something closer to a terawatt. And 100 gigawatts is already a difficult sentence to say out loud.
Picture 100 large nuclear power plants running flat out, all at once. All of it aimed at a single mirror, the size of a bedspread, for 10 minutes. There is no headroom in that number. There is no version of this where somebody says, let's just make it a bit heavier and see how it goes. So the mass budget is a tyrant. 1 gram, and out of that gram we have to build a functioning interstellar spacecraft. There are prototypes. One of them is a silicon wafer about 100 millimeters across, which is around 4 inches. A disc you could cover with your palm. It's 1/10 of a millimeter thick, thinner than a credit card, and even that was too heavy. So it's been plasma etched from behind into a honeycomb, a lattice of hollow cells, removing material until the number came down to 1 gram. On that wafer goes everything. A camera, a star tracker so it knows which way it's pointed, a power source, most likely a small pellet of radioactive material giving off heat,
a laser to talk to Earth, thrusters to hold its attitude, and whatever protection the craft is ever going to have, because there won't be any more added later. Hold a paperclip in your hand. Feel how much it doesn't weigh. That's the spacecraft. All of it. The consequence is worth stating plainly here, because it governs every problem we are going to look at for the rest of tonight. Any solution to any problem on this mission has to fit inside the paperclip. We can't add armor. We can't add a spare. We can't add a backup system or a redundant computer or a thicker wall. We can't add a repair kit or a second camera in case the first one fails. There's no crew, so nobody fixes anything. There's no fuel, so it can't slow down. And it can't turn around, and it can't dodge. It leaves, and it holds whatever it was holding when it left, for 20 years. And there's one more thing the gram takes away. People find this one hardest to sit with. The craft can't stop. Slowing down would mean carrying something to slow down with, and there's no mass for it. So the probe doesn't arrive at Alpha Centauri. It goes through, at the same speed it's been holding for 20 years, and out the far side. And then it keeps going. Forever. Everything the mission exists for happens during that one pass. 2 decades of flight for a single crossing, and afterward, the craft continues into empty space for the rest of time. Nothing gets a second attempt. Whatever the camera sees, it sees once. Whatever breaks, stays broken. And whatever the dust does to it along the way, it does quietly, with no one able to look. Decades before anyone on Earth could possibly find out. So there's the object. A paperclip's worth of silicon moving at 37,000 miles a second on its own for 2 decades. Now put that paperclip in front of a grain of dust. The first thing to understand is that at these speeds, the word collision stops meaning what it normally means. Nothing bounces, nothing dents. What happens is closer to a detonation. And the reason is a piece of arithmetic that's been sitting in physics textbooks for a century. Kinetic energy goes up with the square of speed. Double the speed and the energy quadruples. Climb to 1/5 of light speed and something changes. The energy stored in ordinary matter, purely by moving, goes outside normal experience. Here's the number. At 1/5 of the speed of light, any material at all carries more energy per gram than high explosive does. Roughly 400 million times more. Not 400 times. 400 million. Sit with that, because it's the hinge of the entire evening. Gram for gram, a lump of rock moving at that speed is 400 million times more energetic than the same weight of TNT. It doesn't matter what the rock is made of, there's no chemistry involved. The energy isn't stored in the bonds, it's stored in the motion, and the motion is the same for granite, for graphite, for a snowflake, for anything. So let's put actual grains into that. A typical interstellar dust grain weighs about 3/10,000ths of a billionth of a gram. Write that out and it's a decimal point followed by a long run of zeros. It's a mass that no scale in your house could measure, and no scale in most laboratories could measure either. At 1/5 of light speed, that grain arrives carrying about half a joule. Half a joule is roughly the energy it takes to lift an apple onto a table. That doesn't sound alarming, and on its own it isn't. But the apple is being lifted over the width of your hand. The grain delivers all of it into a spot smaller than a single red blood cell. And it does that in less time than light takes to cross the width of that spot. Energy isn't dangerous. Concentrated energy is. And that's the typical grain, the one the models say is common. Now take one of the bigger ones, a grain weighing a single nanogram. 1/1000th of a gram, still far too small for your eye, still nothing you could feel on your fingertip. At 1/5 of light speed, it arrives carrying about 1800 joules. It arrives with the energy of a rifle bullet. That's the whole thing. One grain, nothing else has to go wrong. And it doesn't behave like a bullet, which is the part that took people a while to work out. A bullet is slow enough that materials get to act like materials. Metal deforms, energy spreads, things bend before they break. At 37,000 miles a second, none of that happens, because there isn't time for it to happen. A 1-micron grain crosses the full depth of itself in about 1/10 of a picosecond. That's 1/10 of a millionth of a millionth of a second. In that interval, sound hasn't moved across a single atom. The surface it's hitting doesn't know it's been hit yet. Nothing in the target has any opportunity to behave like a solid object. And the grain doesn't stay a grain either. The energy of the impact is enormously larger than the energy holding the grain's own atoms together. So on contact, it stops being a piece of rock. It becomes a cloud of bare nuclei and loose electrons, all still traveling forward together. What happens next unfolds in stages, and the stages are worth going through slowly. The electrons go first. They're light, so they take off through the target material, ionizing atoms as they go. Their energy goes sideways, into a narrow cylinder along the impact track. That cylinder heats, not gradually, the way a stove heats a pan, but almost instantly, because the deposit is finished before heat has any chance to conduct away. Within that cylinder, the temperature climbs past the point where the material can hold together as a solid, then past the point where it holds together as a liquid. The bonds simply stop existing. The matter in the cylinder converts to vapor and leaves, all at once, outward and backward. What's left behind is a crater. Around the crater in a wider cylinder, the material got hot enough to melt, but not hot enough to leave. It cools again in a fraction of a microsecond, and when it refreezes, it isn't the same material it was. The structure has been rewritten. Whatever properties the engineers designed in, the reflectivity, the conductivity, the strength, that patch no longer has them. And it works both ways, which people miss. From where the spacecraft sits, the ship is standing still, and the grain is what comes in at 37,000 miles a second. From where the grain sits, the grain is standing still, and the ship is what arrives. Physics doesn't take sides between those two views. There's no version of this in which the small object is the victim. Both of them are destroyed completely in a stretch of time too short to measure with any instrument we know how to build. So the projectile is not a scratch. It isn't a dent or a chip or a pit. It's a small explosive charge delivered with no chemistry in it, and the explosive is nothing but the speed. There's no fuse, there's no charge, there's no chemistry at all. There's only the number. That's the first place the arithmetic broke. One of those is survivable. Craters are survivable. Spacecraft have taken hits and kept flying. So the question that matters isn't what one grain does. It's how many grains are out there on the way. So let's count them. We know the mass density of dust in the local interstellar medium reasonably well. Assume that mass is packed into micron-sized grains, and we can work out how many sit in a given volume. The answer comes out at around 300th of a millionth of a grain per cubic meter. Then we sweep a surface through it for a light year and see how many it runs into. The published figure is on the order of 30,000 impacts on every square centimeter per light year of travel.
30,000 hits spread over a square centimeter works out to a mean spacing between impact points of about 60 microns. A human hair is 70 microns across. So after 1 light year, the average distance from any crater to the next crater is smaller than the width of a single hair. Not somewhere on the surface. Everywhere on the surface, uniformly, across the entire face. And the trip is longer than 1 light year. It's 4.37 of them. Multiply through and we're at something like 130,000 hits per square centimeter by the time it arrives. Now do the last multiplication, because this is where it gets away from you. Take the sail. Call it 10 square meters, which is on the low side of the design. 10 square meters is 100,000 square centimeters. 100,000 times 130,000 hits on each one. That's about 13 billion impacts on the sail alone. 13 billion small explosions, each one a crater ringed by melted rock, spread across a mirror thinner than a soap bubble. 20 years of that, with nobody watching and nothing to be done about any of it. Except that number isn't firm. It isn't firm at all, and the softness matters more than the size. Other published estimates for the same trip come in far lower. One figure quoted for the mission puts it at around 1,000 impacts per square centimeter over the whole crossing. That's counting grains above 1/10 of a micron. 1,000 or 130,000. Same journey, same physics, different assumptions about what's out there. Hold that gap in mind because it's going to widen. There's one more thing worth separating out here. The chip and the sail stop being the same problem at this point, and they stay separate for the rest of the night. Flown edge-on, the wafer barely presents anything. Its frontal area is a fraction of a square centimeter, a sliver about as wide as a grain of rice. Run the same arithmetic across it, and we land somewhere between 110,000 craters over the entire crossing. It depends on which of the two estimates we believe. A few hundred pits on a chip is survivable, as long as none of them lands on the camera or the transmitter or the one line of circuitry the mission depends on. The sail is a different animal, and the reason is built into what a sail is. It has to be huge. Being huge is its entire function. We can't shrink it, hide it, or angle it away because it exists to catch light across as much area as possible. That asymmetry runs underneath everything from here on. The part of the spacecraft we can make small is the part that could take a hit. The part that can't be made small is the part that has to catch the light. But take the higher number for a moment and picture the object at the far end, not a mirror. Something closer to a screen or a piece of gauze with a hole punched through it. For every stretch of surface narrower than a hair, light would go straight through. Reflectivity, which is the only reason the sail exists, would be gone. Except that's not where the sail dies. The sail probably dies much earlier than that and much closer to home. Now let's come back to the launch. Interstellar space is clean. The inner solar system is not. We live inside a flattened cloud of dust shed by comets and asteroids over billions of years. The zodiacal cloud. Near Earth's orbit, it's thick compared to anything outside the heliosphere. For the smallest grains, the number density near Earth's orbit runs hundreds of times higher than anything out in the interstellar medium. For a 10 square meter sail moving through that, an encounter happens roughly every 3 seconds. Across the whole acceleration run, out to 1/10 of the distance from here to the Sun, the sail meets 1,000,000 grains. 1,000,000. Before it has left the neighborhood. And the thing that kills it isn't the impact. There are 2 ways a grain ends up resting on a sail, and neither is easy to prevent. The first is that it was already there. No clean room is perfect. This object has to be manufactured, folded, packed onto a rocket, carried to orbit, and unfolded again by machinery. Every one of those steps is a chance for a grain to land somewhere and stay. The second is that it arrives during the run. Near Earth's orbit, dust is moving at around 20 kilometers a second relative to the sail. That's fast by any ordinary standard. It's also 1,000th of the speed we've been discussing all evening,
And at a thousandth of that speed, the physics is completely different. Damage assessments of thin metal sheets struck at those velocities suggest that much of the smaller material doesn't punch through at all. It embeds. It buries itself in the surface and sits there. So the impact it survives plants the thing that kills it.
In 2023, a team ran a set of simulations that asked a question nobody had bothered with. Not what happens when a grain hits the sail at speed. What happens when a grain is simply lying on the sail, stuck to it, embedded in it, while the laser is on? To see why that's dangerous, we have to know what a light sail is fighting. It sits in a beam of about a gigawatt on every square meter, the output of a large power station, landing on a patch you could stand on. There's no air, so it can't cool by convection. There's nothing touching it, so it can't cool by conduction. The only way it can shed heat is by radiating it away as infrared. That's it. So the entire design depends on reflecting almost all of the light and absorbing almost none. Even with a sail that reflects 99.9%, the sliver of light leaking through is still a serious heat load. And a dark carbon grain sitting in that beam isn't reflecting anything. It's absorbing. The flux hitting it matches the radiated power of a surface at around 12,000 Kelvin. Twice as hot as the surface of the sun. So the grain heats. It conducts that heat into the structure immediately around it. And silicon-based sail structures have a threshold, a temperature above which they start absorbing more energy than they can possibly radiate away. That threshold sits at about 516 Kelvin, 469 degrees Fahrenheit, or 243 Celsius. Not much hotter than a domestic oven. The simulation started everything at room temperature and switched the beam on. 14 microseconds, 14 millionths of a second. That's the interval from the laser coming on to the material next to the dust grain crossing that threshold. And after it crosses, the process stops needing the dust. The structure is now absorbing more than it emits, so it heats faster, so it absorbs more, so it heats faster still. Silicon melts. The silica supporting it evaporates out from underneath. The molten silicon left standing is now thermally cut off from everything around it, so it evaporates in turn. Meanwhile, the edge of the hot patch is hitting its neighbors past the same threshold, and they go, and their neighbors go. The simulation found no mechanism that stops it. The hot zone spreads outward without limit until it reaches the edge of the sail, and the sail is gone. 1 grain of soot. There's a size threshold, and it's low. Grains with a radius under about 350 nanometers don't have enough absorbing area to start the cascade. Above that, they do. And when we work backward from how much heat the whole sail can dump, we get a cleanliness requirement that's difficult to believe. The total dust coverage on a 10 square meter sail has to stay under 1 square millimeter. That's 1 part in 10 million by area. Picture the floor of a small room. You're allowed 1 pinhead of dust on it, total, in the whole room. If there are 2, you lose everything. Now build that in a factory, fold it, put it on a rocket, fly it to orbit, unfold it, and hold it to that standard while 100 gigawatts arrives. There are proposed fixes, and they're clever. One is to add a layer 6 nanometers thick of a material that spreads heat sideways very well. The energy from any single grain then gets smeared over a wide enough area to radiate safely. 6 nanometers adds only about 1% to the sail's mass, which for once is affordable. The other is odder and more interesting. We cut the sail into roughly 10 million separate tiles, each about a millimeter square, and we join them with deliberate weak points, fuses. When a tile goes into runaway, the fuse around it evaporates first. The burning tile detaches and drifts away on its own before it can take the rest with it. We accept that we'll lose tiles. We design for it. 10 million tiles, a million impacts, and we plan on ending the run with 90% of the MNRAS. That's the second place the arithmetic broke. The most likely way the sail dies isn't the grain hitting it at a fifth of light speed. It's a grain that was already sitting there, doing nothing, at rest, in the 10 minutes before the journey even starts. All of which raises the obvious question, and it's the question that runs underneath everything from here on. How well do we actually know these grains? So let's consider what we physically held in our hands. The answer is a mission that launched in 1999. Its main job was a comet,
and it did that job. It flew through the coma of Wild 2 and caught cometary grains in a collector filled with aerogel. That's a solid so light it's mostly air. But the collector had two sides. The other side, facing outward, was there to catch interstellar dust drifting through the solar system. 132 aerogel tiles laid out in a mosaic about the size of a tennis racket, with strips of aluminum foil between them. In 2006, the capsule comes down under parachute in the Utah desert. And then the hard part starts. Because the grains are microscopic and the aerogel is a three-dimensional block, and nobody has any idea where in that block to look. So the team scans the tiles layer by layer under a microscope. The scans become short movies that focus down through the depth of the gel. Then they go on the internet. About 30,000 volunteers sign up. Ordinary people at home on their own computers. Between them, they run more than 100 million searches through those images. They are looking for the faint track a grain leaves as it slows through the gel. One of them, in England, finds a candidate and learns about it 4 years later in an email. Out of 100 million searches, they find 69 tracks. Most of those turn out to be spacecraft debris, or contamination, or fragments carrying aluminum. Aluminum doesn't occur as a metal in space, so it gives itself away. After all the eliminations, 7 grains are left. 7 candidate grains of contemporary interstellar dust. That's what the human species physically has of the material we've been talking about all evening. 3 of them are large by these standards, about 2 microns across, weighing 3 to 4 trillionths of a gram. 2 survived intact, slowed gently enough by the aerogel to be recovered and examined. The third came in too fast and vaporized on the way in, leaving nothing but a hole 35 microns long. The 4 smaller ones were found in the aluminum foil, which had never been intended as a collector at all. Somebody thought to look at it anyway. The craters there measure about 280 nanometers across. 250 of them, side by side, would span a single human hair. Be careful about what that sample is and isn't. The number 7 is carrying an enormous amount of weight in this story. 7 grains is not a population. We can't fit a size distribution to 7 objects. We can't say how common the large ones are, or whether there's an upper limit, or where that limit sits. What 7 grains tells us is that the material is real, and that it's reachable, and what a handful of individual pieces of it happen to be made of. That's genuine knowledge, and it was won the hard way, by 30,000 people staring at grey images for years. It just isn't the kind of knowledge we need to fly through the stuff at a fifth of light speed. The people who ran that search knew it perfectly well. They said openly that they expected to end up with no more than a dozen grains from the whole collector. A millionth of the mass of cometary material the other side of the same instrument had caught. A magnificent result, and a very small one at the same time. And then the 2 intact grains were analyzed, and they didn't match. The model said interstellar grains should be irregular and amorphous. Lumps with no ordered internal structure, battered by millions of years of shocks and radiation. What came back was fluffy, porous, more like a snowflake than a pebble. And inside both of them, sitting in the middle of the amorphous material, were crystals. Olivine, a magnesium-iron silicate with an ordered lattice. Crystals do not survive the interstellar medium easily. They shouldn't be there. The entire physical human sample of the dust between the stars is 7 grains. The 2 largest came back with a mineral structure nobody predicted. And nobody has explained where the crystals came from, or how they lasted, or how common they are. 7 grains, and not one of them was large enough to matter. That's a strange thing to say about the only samples we have. But there's a threshold buried in this problem, and everything turns on where it sits. Below the threshold, dust is erosion. It scars a surface, takes bites out of a sail, and wears the mission down slowly. Above the threshold, dust stops being erosion and becomes an ending. So let's find that number. We got it in 2017, and the question behind it is simple. How large does 1 grain have to be before a single collision destroys the whole spacecraft outright? For a craft weighing 1 gram, the answer is about 15 microns. 15 microns is a fifth of the width of a human hair. It's roughly the size of 1 particle of talcum powder. Shake powder out of a bottle sometime and watch the haze hang in the bathroom light. You're looking at millions of them. You breathe some in, you don't notice because there's nothing to notice. That size is fatal for a reason, and the reason isn't the logic of a crater. A small grain dumps its energy near the surface. The material right there vaporizes, a pit forms, and the rest of the spacecraft never learns about it. A large grain doesn't stop near the surface. The atoms in its interior are shielded by the atoms in front of them, so they keep going. The energy goes deep, and it spreads through the entire volume of whatever it hit. At 15 microns, the arithmetic crosses a line. That grain arrives carrying somewhere around 80 kilojoules, which is about the food energy in a single teaspoon of sugar. It's such an ordinary number that it looks like a mistake next to the word destroyed. So, let's deliver the teaspoon properly, all at once, into 1 gram of silicon in a fraction of a billionth of a second. 80 kilojoules is several times the energy it takes to boil the entire spacecraft away. Not melt it, boil it. Every atom in the chip lifted past the bond that holds it to its neighbors and gone as vapor. And the threshold drops as the craft gets smaller. Shrink the vehicle to a centimeter long and a millimeter across, and a grain of about 4 microns finishes it. There's a second thing about dust worth putting on the table now. It explains why 1% of the mass causes most of the trouble. Dust holds nearly all of the heavy elements out there. Iron, magnesium, silicon, most of the carbon. Those atoms aren't drifting around loose as gas, they are locked into grains. So a dust grain isn't a scaled-up gas atom, it's a package. A micron-sized grain contains something like 10 billion heavy nuclei, and they all arrive at the same instant, on the same square micron of surface. The gas delivers its atoms one at a time, spread over 20 years. The dust delivers 10 billion of them in a single blow. That's the difference between an abrasion and a detonation, and it's why everything hinges on how many grains there are and how big they get. So the whole question turns into a counting question. How many 15-micron grains lie between here and Alpha Centauri? The standard answer is close to none. We build our picture of interstellar dust almost entirely out of starlight. Light from a distant star passes through a cloud on its way to us. Some wavelengths get scattered and absorbed more than others, and the star looks redder than it should. The exact shape of that reddening depends on the sizes of the grains doing it. Then we work backward from the color to the population. Decades of that work gave us size distributions that agree with each other on the shape. Most of the mass sits below a quarter of a micron. Above that, the numbers drop off exponentially. Above a third of a micron, there's very little left at all. 15 microns is 40 times past the point where that curve has already collapsed. By the standard distribution, the grain that ends the mission doesn't exist along this path. Not rare, effectively absent. The comfortable answer held for a long time, and the mission was designed around it. But there's a weakness in the method, and it needs naming now because it comes back. Starlight tells us about grains that interact with starlight. Small ones do that beautifully. A quarter-micron grain is close in size to the wavelength of visible light, so it scatters strongly, and there are vast numbers of them. Together they dominate the whole signal. A 15-micron grain is enormous by comparison. Individually it blocks more light, but there are so few of them that they barely touch the signal at all. So the method that built our entire picture of the dust is nearly blind in exactly the size range that decides whether the spacecraft lives. The method isn't wrong, it's answering a different question than the one we're asking. And there's a further thing about that distribution that's easy to miss. It isn't a law, it's a fit. Somebody chose a functional shape, added a cutoff, and tuned the parameters until the curve reproduced the observed reddening. That's good science, and it works well for what it was built to do. But the cutoff isn't the measurement, it's the shape that made the fit come out right. So the claim that the lethal grain effectively doesn't exist comes down to this. Our best fit to a different measurement puts almost nothing up there. Those are not the same statement. And the gap between them is where a spacecraft lives or dies. And then the instruments started finding them. The date is February 8, 1992. A spacecraft about the size of a small car swings past Jupiter. It uses the planet's gravity to throw itself clean out of the plane of the solar system, onto an orbit tilted almost 80 degrees. It's going to fly over the poles of the Sun. Nobody has ever done that. It carries a dust detector, and within a year of the flyby, that detector starts recording something that shouldn't be there. Grains roughly a micron across, moving at 26 kilometers a second or faster, moving the wrong way, against the direction the planets travel, on paths that never close into orbits. They aren't circling the Sun. They're passing straight through and out the other side. They all arrive from the same direction. And that direction matches the flow of interstellar gas through the solar system. A twin instrument aboard the Jupiter orbiter sees the same population and confirms it. That was the first time we caught contemporary interstellar dust inside our own solar system without ambiguity. It closed the question that had been open for decades. The dust gets in. Some of it anyway. We kept watching with that spacecraft until the end of 2007, 16 years of continuous monitoring. Around 1,000 interstellar grains measured and weighed one by one. And the population it handed back did not match the one we'd built from starlight. The measured masses ran up to about a 10 billionth of a gram. Put a single grain of table salt on your palm, you can just barely feel it sitting there. That crystal weighs around 60 millionths of a gram. So these interstellar grains come in at something like a 600,000th of 1 grain of salt. Tiny. And also far bigger than the models had room for. Later analysis of the local dust pushed further still, out to grains of several microns across. There's something else in that data worth flagging, because it shows how unsettled the ground is even where we do have measurements. The early analysis implied a certain amount of dust per unit of gas in the local medium. That ratio came out higher than astronomical observations suggested. It looked like the dust was concentrated in our immediate neighborhood. Then, a fresh analysis of the full 16 years, published in 2015, revised the local dust density downward by a factor of 3. Not a small correction. 3 times less dust from the same instrument, from the same grains, reprocessed. Those are the numbers underneath all of this. Now for a second line of evidence, and it needs careful handling. The most dramatic of them and the least secure. Through the 1990s, a radar array in New Zealand tracked meteors entering the atmosphere and measured their orbits. It could see grains down to about 20 microns in radius. In a survey published in 2000, here's what it reported. A population of meteoroids on unbound orbits arriving from outside the solar system entirely at sizes of tens of microns. And inside that population, an apparent stream, tightly grouped on the sky, coming from the direction of a nearby young star with a bright disk of dust around it. If that reading holds, then grains far above the lethal threshold aren't merely present. They arrive in organized streams from identifiable sources, and the spacecraft could fly straight into one. It may not hold. A reanalysis a few years later found the arrival direction didn't match where grains from that star should come from. The radar itself stopped operating in 2000. Later searches with other radars hunted larger grains instead. They sifted through millions of meteor orbits and turned up only a handful of candidates, which the teams put down to measurement error. So we are left with a claim, a dispute, and no instrument currently running that could settle either one. There's one more caveat, and it's the broadest of all of them. Everything so far assumes the gas and the dust are mixed the same way everywhere. The standard ratio, about 100 parts of gas to 1 part of dust by mass, is a galactic average. Over 4 light years, nothing guarantees it holds. Our own local cloud may be different. It's a small region, it has its own history, and nothing requires it to be typical. So even a perfect measurement of the dust here wouldn't settle what's waiting a light year out. That's the third place the arithmetic broke, and it's the most uncomfortable so far. The size that kills the spacecraft sits exactly in the gap between our 2 ways of knowing. Starlight modeling is blind up there, and it tells us nothing should exist. Direct detection keeps finding things up there, and it can't tell us how many. The one band of grain sizes where the answer decides the mission is the one band where we have no reliable count. And remember what's being hit: 1 gram total. There's something worse about those direct detections. Every single one of them was made inside a filter, and the filter is us. The sun does two things to a grain that wanders in from outside. First, it charges it. Ultraviolet light knocks electrons off the grain's surface. The grain ends up carrying a net positive charge. Second, the sun blows a magnetic field past it. The solar wind streams outward in all directions and drags the sun's magnetic field along with it. A charged particle crossing a magnetic field feels a sideways push. So does a charged grain of rock. Whether that push matters comes down to one ratio: how much charge the grain carries against how much mass has to be moved. Charge collects on the surface, so it scales with area. Mass fills the interior, so it scales with volume. The smaller the grain, the more charge it carries for every unit of mass, and the harder the field can steer it. Below about 100 of a micron, grains never get in at all. They're carried around the outside of the heliosphere, the way leaves go around the rock in a stream. Between there and roughly 1/10 of a micron, they're heavily thinned. Only the larger ones come through more or less undisturbed because they're too heavy to push. And the steering keeps changing sign. The sun's magnetic polarity flips about every 11 years, which makes a full cycle of 22. In one half of the cycle, the field funnels grains inward. In the other half, it shoves them away. The smallest grain that can reach any given distance depends on which half of the cycle is running. There's one more wrinkle, and this one really bites. A grain takes decades to cross the heliosphere. It enters at the boundary, gets pushed around by a field that keeps reversing, and only then reaches an instrument somewhere near the planets. So the grains we catch today didn't experience today's magnetic configuration. They experienced the one from 20 or 30 years ago, and several others on the way in. We can't even correct for the filter cleanly. The filter has a memory. So look what all of that does to every sample we've talked about. The 16 years of measurements, the recovered grains in the aerogel, all of it collected inside a magnetic sieve in one phase of one cycle, tilted by construction toward the large end of whatever is out there. It doesn't mean the measurements are wrong. Every one of those grains is real, and it was correctly weighed. It means the population they represent isn't the population outside. Imagine judging what's in a bag of flour by examining only what stays behind in the sieve. You'd learn a great deal about the lumps and nothing whatsoever about the flour. Now imagine the sieve quietly changes its mesh every 11 years, and nobody sends word when it does. And notice which way that bias runs, because it cuts both ways. The sieve keeps the big grains and blocks the small ones. So the population caught inside is tilted toward exactly the sizes that frighten us. That could mean the danger is overstated. The large grains we keep catching might be an artifact of the filter that produced them. Or it could mean the danger is entirely real, and this is the one place it shows up clearly. To tell those apart, we'd need the distribution outside the bubble, the very thing in question. So the obvious move is to go outside and measure it there. If this part of the journey has unsettled you the way it unsettled me when I first read it, please like the video and subscribe. It helps more than you'd think.
Voyager 1 crossed out of the solar wind's bubble in August of 2012. It was 121 times the Earth's distance from the Sun at the time. It's been in interstellar space ever since. It is the only object we have ever built that sits inside the medium we are discussing. It does not carry a dust detector. Nobody made a mistake. The spacecraft launched in 1977. The instrument list was built for the outer planets, and a dedicated dust counter didn't make the cut. The pioneers before it did carry dust detectors, and those stopped returning useful data around 18 times the Earth's distance from the Sun. So this is how we listen for dust out there now. There's an antenna on board for measuring plasma waves. It was designed to study the magnetic environments of Jupiter and Saturn. When a grain strikes the spacecraft body, it vaporizes and ionizes on contact. A small cloud of plasma expands away from the impact point. As that cloud washes over the antenna, it produces a voltage pulse with a rise time of about 10 microseconds. Sharp, distinctive, easy to pick out of the noise. That's the dust instrument, an antenna built for something else, listening for a click. It's a little like diagnosing an engine with the hood shut. By ear, something happened, nothing beyond that.
Inside the solar system, it hears a few of those clicks an hour, out past the boundary, a few a year, and the pulse tells us a grain arrived. It doesn't tell us how heavy the grain was, or how fast it came, or what it was made of. We have never measured it, not properly, not once. We have no measurements of dust near or beyond the edge of the heliosphere. Nothing good enough to fix a grain's mass, or its speed, or what it was made of. This is the evidence we have. That is the foundation the entire risk calculation is standing on. 25 trillion miles of it, and we've never held a proper instrument up to any of it. The same antenna has given us other things, and it's worth being fair about that. From the plasma oscillations it picks up, we've measured the electron density outside the heliopause and watched it climb as the spacecraft goes deeper. That's real interstellar science, done with a spacecraft older than most of the people reading its data. It just isn't dust. There's also a clock running on it. The power supply aboard that spacecraft fades by a few watts every year. Instruments have been switched off one at a time to stretch what's left. Sometime in the next decade or so, the last of them goes quiet. And when that happens, we'll have nothing inside the interstellar medium at all. No antenna, no counter, no clicks. Modeling from a distance is all that's left. And it stays that way until something else gets out that far. Nobody has funded that. Nobody has built it. There is one dedicated dust counter out there, and it exists because of students. New Horizons carries an instrument built and operated by an undergraduate team. It's the first dust detector ever flown beyond 18 times the Earth's distance from the Sun, and it's been counting since 2006. And what it reports, out past 55 times the Earth's distance, is more dust than the models predicted. The counts keep running above the curve. The gap keeps widening as the spacecraft goes out. Nobody is certain why. Sit with that for a moment. This is our own solar system. We have theories about it and a working instrument physically inside it. And our models are undercounting the dust. There's one more, and it's new. In September of 2025, a spacecraft launched carrying an instrument built to catch interstellar grains and read their chemistry. First data came back in December. It now holds position about 1 million miles from Earth on the sunward side, with an aperture open to the incoming flow. When a grain hits it, the grain vaporizes into a cloud of ions. The instrument reads those ions and works out what the grain was made of. We expect it to catch about 100 interstellar grains a year, roughly 2 a week. That's how fast our knowledge of this thing improves. 2 grains a week, caught one at a time, in a drum-shaped instrument at the far edge of Earth's neighborhood. And the Starship's survival rests on that ledger. So with all of that in hand, what odds would we actually be prepared to write down? The honest answer is already in print, and it's one of the stranger passages in any of these papers. The same 2017 study that gave us the 15-micron threshold also worked out the chance of meeting such a grain. It didn't give one number, it gave 3. Take the standard grain size distribution, the one built from starlight. The chance of hitting a little grain on the way there comes out at about 1 in 10 to the 50th power. That isn't a long shot. That's the number you write when you mean never. Using measured fluxes of interstellar grains instead, the same trip gives about 1 chance in 10 million. And using a model of interplanetary dust fitted to spacecraft data, the answer lands at roughly 1 in 100. 1 in 100 is a completely different world. It's a risk you'd accept for a single probe and lose sleep over for a fleet. Launch 1,000 of them at 1 in 100 and you expect to lose about 10 to a single grain each. Launch 1,000 at 1 in 10 million and not one will ever die that way. Not in the lifetime of the program. Not in the lifetime of the species. Between the two extremes there are 48 orders of magnitude. Same physics, same mission, same paper. 3 assumptions about what's out there, and the answer slides from impossible to routine. So how many spacecraft do we build? How much shielding do we pay for? Who signs the line on the risk assessment? What do we tell the people paying for it when they ask how likely it is to arrive? We can't answer those yet. That isn't a rhetorical flourish. We have not made the measurement those answers depend on. And the fleet doesn't rescue us from that, which is the part people tend to miss. Redundancy protects against bad luck. If every probe carries an independent 1 in 100 chance of being killed, then sending 1,000 almost guarantees that most of them arrive.
It's the whole logic of the swarm, and it's sound. But redundancy does nothing against being wrong. If the real dust population is worse than every model says, then it's worse for all 1,000 at once. They fly the same route, through the same cloud, at the same speed. A systematic error doesn't average out across a fleet, it takes the fleet. The study does point at the one lever that reliably works: shrink the target. The rate of hits scales with the area you present, so a needle-shaped craft with a tiny frontal cross-section runs a very small risk. That works for the chip. What it doesn't work for is already clear.
And there's one more thing missing from all three estimates: the destination itself. The Alpha Centauri system isn't clean. Radio observations have reported belts of cold dust around Proxima. They sit in a band roughly 1 to 4 times as far out as the Earth sits from the Sun. There are hints of a second belt much further out. In 2025, a space telescope looked at the brighter star of the pair in the mid-infrared. It set upper limits on the warm dust close in. Upper limits, not measurements. The same observations turned up a candidate giant planet in the habitable zone. It's the most interesting thing anyone has found there. It's also one more object to fly past. At 1/5 of light speed, the probe covers the distance from here to the Sun in about 42 minutes. It crosses the entire system in a couple of days. 42 minutes, long enough to cook dinner. And there's the encounter. It happens once, after 20 years of flying.
Nobody has put a dust density on that crossing. It isn't in the risk calculation because there's nothing to put in. So the probe arrives at full speed in the one region of the whole journey where the dust is almost certainly thickest. And we have no idea what's waiting there. And all of this has been about dust, which is 1% of what's out there. The other 99% is gas, and so far, we've been ignoring it. By number, roughly 9 atoms in 10 are hydrogen, about 8 in 100 are helium. The rest is a trace of everything else scattered thin. Standing still, that gas is nothing. It's colder and emptier than any vacuum a laboratory can produce. A hydrogen atom drifting past you carries less energy than a mosquito landing on your arm. Now move through it at 1/5 of the speed of light. In the spacecraft's own frame, every one of those atoms becomes a projectile, and the electrons get stripped away instantly on contact. So what actually strikes the material is the bare nucleus. At 1/5 of light speed, a hydrogen nucleus arrives carrying about 19 million electron volts. Helium comes in around 75 million. Oxygen close to 300 million. For scale, the photons in a dental X-ray carry a few tens of thousands of electron volts. What hits the front of this spacecraft is 1,000 times more energetic than that. And it isn't light, it's a nucleus with mass arriving continuously for 20 years. Now for the count. Over the crossing to Alpha Centauri, every square centimeter of the leading edge takes somewhere around 4 billion hydrogen nuclei. A square centimeter is the tip of your little finger, and this is the part that changes how we think about the entire problem. That total does not depend on how fast the spacecraft goes. The number of atoms it runs into is set by how many atoms lie along the path. Cross 4.37 light years, and the same column of gas gets swept up, whether the trip takes 20 years or 2,000. Slowing down does not buy us fewer hits. That's the 4th place the arithmetic broke. Going slower doesn't reduce the number of impacts at all. It only reduces the energy of each one. The count is fixed by the distance, and the distance is not negotiable. There's one stretch of the route where that column gets thicker, and it sits at the far end. Where a star's wind pushes out against the interstellar gas, the gas piles up. It gets compressed and heated into a shell wrapped around the whole system. We have one of these ourselves, and we've detected it from the inside. Around Alpha Centauri, models put that shell near 30,000 Kelvin, with the density raised above the surrounding medium. The probe would cross it near the end of the trip, at full speed in a matter of hours. No instrument has ever been through one. If we ever fly this mission, that crossing becomes the first look anyone has had inside a hydrogen wall, and it happens in the final hours before arrival. So where do all those nuclei end up? About 2 millimeters in for graphite or silicon. And the physics here has a small piece of elegance in it, and it's very bad news.
Helium loses energy roughly 4 times faster than hydrogen as it plows through a solid. But at the same speed, helium also carries about 4 times more energy because it's 4 times heavier. The two effects cancel almost exactly. Hydrogen and helium traveling at the same speed stop at the same depth. They don't spread themselves through the material, they pile up together in one thin buried layer about 2 millimeters below the surface over 20 years. Gas atoms buried in a solid don't dissolve into it, they find each other. They collect into bubbles, the bubbles pressurize, and as more gas keeps arriving, the pressure climbs. Eventually, the bubbles nearest the surface push the material above them outward. It lifts, it domes, it bursts. Then the layer above flakes off.
Anyone who's watched old paint lift off a hot pipe knows the shape of it. Blisters first, then flaking. The difference is where it starts. This erosion doesn't begin at the surface. It begins underneath, in a buried layer, out of sight and out of reach, and works its way up. And every blister that bursts throws material off in one direction, which puts a small twist on the spacecraft. Thousands of little shoves over 2 decades, every one of which has to be corrected somehow. That's the material. Now the electronics. A 19 million electron-volt proton doesn't only stop. On the way in, it produces secondary particles, and those are their own problem. Neutrons come off when protons and helium nuclei strike the nuclei of the shield. Some of those shield nuclei break apart entirely, and a fraction of the shield becomes radioactive, activated by the bombardment, so the spacecraft ends up carrying a low-level source of its own. There's also light. Charged particles slowing down inside a solid emit radiation. And here, that radiation lands in the X-ray band. The front edge of this spacecraft is, in a small way, an X-ray tube that runs for 20 years and can't be switched off. Add it all together and we get a dose. Over a 30-year mission, in thin silicon, it works out to roughly 35 million rads. Ordinary commercial chips fail at around 10,000 rads. Divide it out. The processor in the phone in your pocket would survive about 3 days of interstellar flight. Hardened parts do far better. Chips designed for particle accelerators take more than 10 million rads in a year, so the number isn't automatically fatal. But every one of those parts is heavier, slower, and larger than its commercial equivalent. Every gram of that comes out of a budget that doesn't have one. And one comparison puts the whole thing in perspective. Galactic cosmic rays over those same 30 years deliver about 200 rads. 200 against 35 million. Cosmic rays are the thing we worry about in deep space. They are the reason spacecraft carry shielded electronics and the reason long human missions are hard. On this trip, they are a rounding error. The interstellar gas is nearly at rest and nearly harmless. It does close to 200,000 times more damage, purely because we are the ones moving. There is a standard answer to all of this, and it's elegant enough that it very nearly works. Fly edge on. Here's why that helps. In the rest frame of the interstellar medium, the gas drifts in every direction at a few miles a second. It comes from everywhere, isotropic in the textbook sense. But the spacecraft isn't in that frame. In its own frame, it's standing still, and the entire medium is coming at it head-on at 37,000 miles a second. Everything else those atoms were doing is negligible beside that. So what strikes the ship isn't a spray, it's a needle. Almost all of the flux arrives within about a 10,000th of a radian of dead ahead. A 10,000th of a radian is roughly the angle a dinner plate makes from 2 miles away. That's how tightly the incoming fire is collimated, which suggests an obvious defense. Turn the wafer sideways, so it flies like a coin thrown edge first. Those huge flat faces then see almost nothing at all. Then put a small lip along the leading rim, standing up into the beam. Anything arriving in that narrow cone strikes the lip instead of the electronics. A rain guard on a car door works the same way. Rain comes down almost vertically, so a strip of plastic an inch wide keeps a whole window dry. The numbers work out surprisingly well. For a wafer about 10 centimeters across, that lip needs to stand roughly 1/10 of a millimeter high, about the thickness of a sheet of paper.
Front to back, it needs about 3 millimeters, which is what it takes to stop a 19 million electron-volt proton. The mass comes to around 0.2 of a gram. 0.2 of a gram out of 1. A fifth of the entire spacecraft spent on a lip you could barely see with the naked eye. There's a bonus in the geometry too, and it's worth taking. Because everything arrives so close to head-on, a thin disk tilted even slightly presents a much longer path through its own material. The disk and any coating on it behave as though they were far thicker than they are. For once, the physics is helping. And all of it would work as long as the spacecraft holds still. It won't hold still, and the reason is the medium itself. Every proton that slams into the leading edge knocks electrons out of the material, and some of them escape. The edge loses negative charge and gains positive charge. It keeps gaining until the electric potential is strong enough to hold the remaining electrons in. That charge doesn't spread out over the spacecraft. The incoming particles bury themselves in a shallow region near the front, so the charge stays where it was made, concentrated along the leading rim, which turns the whole spacecraft into an electric dipole, positive at the front, neutral behind. And there's a magnetic field threading interstellar space. It's faint, far weaker than the field of a magnet on your refrigerator door, but it's there, and the dipole sitting in a magnetic field feels a twist, so the craft starts to rock. The calculated period is about half an hour. Work out what that means across the mission. Twice an hour, the flat face swings around and presents itself to the beam. Twice an hour for 20 years. That comes to roughly 1/3 times. Every one of those swings exposes the full face of the wafer to the flux the lip was built to block. And that face is hundreds of times the area of the leading edge. The shield doesn't fail. It simply stops being in front of anything. There's a related problem with thin wafers, which is that a 19 million electron-volt proton goes straight through one. It enters the front, crosses 1/10 of a millimeter of silicon, and leaves out the back. The thinnest parts of the spacecraft take hits on both faces at once, and the count doubles. Try holding a coin edge-on into a strong wind. You can manage it for a few seconds with your fingers. Now do it for 20 years, with no fingers, and with the wind itself shoving you around. One thing here actually doesn't go wrong, and it deserves a mention. A charged object moving through a magnetic field gets bent off its path. So you'd expect the whole trajectory to curve away, and for a small charged craft, that could ruin the aim entirely. Run the numbers and the bend is negligible. The radius of that curve works out to something like 500 light-years. Over 4, the path stays straight enough to hit what we aimed at. So the field doesn't push the ship off course, it only rolls it over. The more expensive of the two problems as it happens. There are answers on paper, and some are good. Small photon thrusters, laser diodes firing sideways, which deliver enough of a nudge to correct for impacts and drift. Miniature ion thrusters, which give thousands of times more push for the same power. Spinning the wafer fast about its own axis so its angular momentum resists the twist. Launching it with a net negative charge so the charging takes longer to build up. Every one of those is a reasonable idea. Not one has ever been demonstrated on a gram-scale spacecraft, in flight, over decades, with nobody able to intervene. So the medium the shield was designed to stop is the same thing that keeps turning the shield away. And no working attitude control system for a 1-gram interstellar craft has ever been built or tested. Which brings us to the shield itself and to the number that ends the design. Suppose we give up on the lip and the clever geometry. Suppose we do what spacecraft engineers have always done and put material in front of the thing we care about. How much material? Independent calculations agree on this, which doesn't happen often in this story. Against dust, the answer is 1 to 3 millimeters of graphite or beryllium. Add the range of the charged particles and it climbs towards 6. 3 millimeters is about the thickness of 2 coins stacked. There's the whole requirement. It isn't exotic material and it isn't very much of it. There are constraints on what the material can be, and they're interesting. It wants to be light, obviously. It also wants a low atomic number, because heavier elements throw off more secondary neutrons when the protons arrive. Carbon does well on both counts. Beryllium does well too, and it soaks up a great deal of heat before it vaporizes, which is why the older studies liked it. And the shield has to be roughly twice as thick as the depth where the protons stop. If it's thinner, the buried gas layer sits close enough to the far side to blister through into whatever is behind it.
On a small enough body, all of this is affordable. Take a needle-shaped craft, a millimeter in radius and 5 millimeters long, roughly the size of a grain of rice. Wrap the front of that in 3 millimeters of graphite, and the shield weighs somewhere between 10 and 50 milligrams. Out of a 1 gram budget, that's 1 to 5%. Fine, buildable. Nobody argues about it. So now the sail. We'll do this multiplication out loud, slowly, because it's the one that ends the argument. Take 10 square meters of sail. Cover it with 2 millimeters of graphite. That's a slab of carbon 10 square meters in area and 2 millimeters thick. It comes to about 20,000 cubic centimeters of material. Graphite weighs a little over 2 grams for every cubic centimeter. Multiply it through, and that shield weighs about 100 pounds. 45 kilograms of carbon to protect a spacecraft that's allowed to weigh 1 gram. That isn't over budget by a margin anyone negotiates. It's over by a factor of about 45,000. We could throw away every instrument, every camera, every transistor, the whole chip. That would free up 1 gram out of the 45,000 we need. One design in history took this problem seriously and paid the bill. Look at what the honest price came to. In the 1970s, a team of British engineers spent 5 years designing a fusion-powered probe to Barnard's star. It was meant to cruise at about 12% of light speed, a little over half the speed we've been discussing all night. Their study is still the most detailed interstellar vehicle design anyone has produced. They included an erosion shield, beryllium 7 to 9 millimeters thick, 32 meters in radius. It weighed 50 tons. That's about a tenth of everything the vehicle carried during the cruise, a tenth of the entire dry mass, spent on a plate of metal whose only job was to be eaten by dust. They proposed something stranger as well. As the probe closed on the target system, the dust would get thicker, so it would spray a cloud of its own dust out ahead of itself. Incoming grains would then detonate in the cloud rather than on the hull. That idea has a modern cousin. Instead of a cloud, you fly a thin foil some distance out ahead of the spacecraft. A grain hitting the foil doesn't get stopped by it. At these speeds, nothing stops anything. But it does get torn apart and ionized, and the pieces spread out across the gap before they reach the ship. What arrives is a diffuse spray instead of one concentrated blow. The catch it always is. That foil has to be carried, aimed, and held in position ahead of a craft moving at 37,000 miles a second for 20 years. And it has to weigh almost nothing. Those are the measures a serious design takes, and the design that took them had 500 tons to work with. That's the 5th place the arithmetic broke, and it's the cleanest of them all. The protection isn't expensive, it isn't rare, it isn't exotic, and nobody has to invent it. 2 millimeters of ordinary carbon would do the job. It just weighs more than the entire spacecraft, by a factor of tens of thousands. So we don't carry it. We fold the sail away instead. That's the published recommendation, and it follows directly. Retract the sail behind whatever protective material the craft can afford. Fly as a needle, long axis forward, presenting almost nothing. Minimize the target, and you minimize the hits. It's the right answer to the question that was asked. And it creates a new problem, which is that the probe now has no voice. The reason is simple. The spacecraft carries a small laser for talking to Earth, running around 100 watts in short bursts. But a laser needs an aperture to send through. The wider the aperture, the tighter the beam, and the more of it lands where you want it. The only wide flat surface on this spacecraft is the sail. The sail is the antenna. So let's follow the signal home. A 4-meter aperture, 100 watts, 25 trillion miles of empty space. And at this end, a 30-meter telescope on the ground, one of the largest anyone has proposed building. That telescope collects fewer than 300 photons per second. 300, individually counted, one at a time. The reading lamp beside you throws out more light in a single flicker than that telescope would gather in a year.
From 300 photons a second, careful encoding gets a few hundred bits per second. In the best theoretical case, maybe 1500. Over a year, that comes to somewhere between 8 and 50 gigabits. Call the low end a gigabyte a year. A couple of hundred phone photographs spread across 12 months. And getting even that much means solving something else first. The probe has to know where to aim. 4 light-years out, Earth is a faint point sitting beside a much brighter one, and both have moved since launch. The craft has to find the Sun, then work out where our planet will be when the beam arrives. Then hold that aim through the whole transmission. It does this with its own camera acting as a star tracker, and with nobody to help. Miss by a small angle at that range, and the beam lands somewhere else entirely. There's no second attempt. By then, the probe is deeper into interstellar space, and the geometry only gets worse. The receiving end at least has an answer. The same array of lasers that launched the thing can be run backward as a telescope, thousands of apertures working together. The engine becomes the ear. That's the entire scientific return, and it only exists if the sail is out. So what does leaving it out cost? Face on, the reflector takes about 4 proton hits every year on every square angstrom of its surface. An angstrom is roughly the width of 1 atom. The sail is a few hundred atoms thick. Over the crossing, every atom in it is struck dozens of times. And that's only the gas. On top of it sits the dust, and we've already seen the range of estimates for what the dust does to a surface that size. The lowest published figure has holes costing about 1% of the sail's area. The highest has a hole for every stretch of surface narrower than a hair. That disagreement is the same one from earlier tonight, and it hasn't been resolved. So, here's the contradiction, stated flat. Leave the sail out, and it erodes, and it fills with holes, and every atom in it gets hammered for 20 years. Folds the sail away, and the probe cannot be hurt. Both recommendations are in the published literature. One paper advises retracting the sail behind protection. Another calculates that gas drag on an open sail is small enough to ignore. It concludes the sail can stay deployed for communication at almost no cost in speed. They cannot both be right, and nobody has had to choose yet, because nothing has been built. And there's a last turn of the screw in this, which has nothing to do with physics. The probe flies for 20 years. It crosses the target system in a matter of days, with the useful part of the encounter lasting minutes. Then it starts transmitting, and the signal takes another 4 years and change to reach us. So the earliest anyone on Earth could hear anything is roughly a quarter of a century after launch. Now suppose the sail tore in the first year. Suppose a grain took the transmitter out in the 5th. Suppose it simply arrived deaf and blind and flew past the planet with nothing working. From here, for 25 years, all of those look exactly like a probe that's fine and still on its way. Silence and success are the same signal until the very end. We need to talk about testing now, because that's how every spacecraft in history has been made trustworthy. Nothing flies untested. Vibration tables shake it the way a rocket would. Thermal vacuum chambers freeze it and bake it. Radiation beams at accelerators fire protons into the electronics until something flips. You reproduce the environment on the ground, you break things deliberately, and then you fly the design that survived. For dust impacts, that means hypervelocity laboratories, and they're real, and they're good. Electrostatic dust accelerators charge a grain and drop it through a voltage. The first one was built in 1962 and pushed iron spheres a tenth of a micron across to 14 kilometers a second. Modern versions run in Colorado, in England, in Germany. They handle grains from 30 nanometers up to a micron at 1 to about 100 kilometers a second. They can select grains by mass and by speed. They fire roughly 1 grain per second. Light gas guns manage 8 to 9 kilometers a second with projectiles from a micron up to about a quarter of an inch. Railguns top out near 6 kilometers a second, and that's after 50 years of trying. The largest pulsed power machine in existence drives thin metal plates to around 50 kilometers a second across less than half an inch of travel. And the fastest condensed matter anyone has ever launched comes from fusion lasers. Ablate the back of a thin plastic foil and it takes off at 700, even 900 kilometers a second. About 90% of the foil is lost in the process, and nobody can say what state the rest is in. That's the record for solid matter of any kind, and it isn't a grain of dust anymore. For something still recognizable as a grain when it lands, the ceiling is the one we started with, 100 kilometers a second. The spacecraft needs 60,000, 600 times too slow. Not 600 times short of comfortable, 600 times short of the number, using the fastest method that exists, on a target we can't properly characterize. And this isn't a funding problem, it's a physics problem, and it closes off cleanly. To accelerate a grain electrostatically, you have to charge it, and there's a ceiling on how much charge it can hold. Push the electric field at the surface past about 1 billion volts per meter, and electrons start tunneling straight out. The grain sheds charge as fast as you add it. That ceiling scales badly. Bigger grains carry less charge for every unit of mass, so the bigger the grain, the worse the ratio gets. Work through it for a single micron-sized grain, at that field limit, aiming for 1/10 of light speed. You need a straight accelerator over 20 kilometers long. 14 miles of tunnel, longer than most subway lines, built to fire 1 grain of dust. Bend it into a ring instead, and magnets have to hold the turn. With fields like the ones in the biggest colliders, the ring comes out around 1,000 kilometers in radius. So there's no laboratory route to the answer, and there isn't a plausible one. And the gap is odder than it looks, because the other half of the problem is completely testable. 19 million electron-volt protons are routine. Accelerators have made them for the better part of a century, and there's a deep body of measurements on what such beams do to solids. A sample can sit in a beamline and take 20 years of interstellar exposure in about 6 weeks. Turn the flux up and the clock runs faster. So the gas problem can be reproduced on a bench, argued over and engineered around. The dust problem cannot be reproduced at all. And it isn't only the impacts. The thermal cascade from earlier tonight, the one that eats the sail, exists so far only inside a computer, which leaves us relying on theory. And the theory has a hard edge in it, closer than it looks. The standard defense against impacts in space is the bumper shield, proposed in 1947. A thin sheet held out in front of the hull with a gap behind it. The incoming particle shatters and vaporizes on the sheet. The debris spreads out across the gap. What reaches the hull is a wide, soft spray instead of a point. It works. It's on the space station right now. It's been validated to roughly 10 kilometers a second. And even below that, it isn't tidy. Take a fixed projectile and raise its speed from 2 to 10 kilometers a second. A shield can go from penetrated to intact and back to penetrated again. Material strength and vaporization trade places as the pressure climbs, and the result oscillates. Above 10 kilometers a second, the data that would let us calculate doesn't exist. Not the equations of state, not the strength models, nothing. And between 10 and 60,000, physics we haven't met is close to guaranteed. Some of the guesses get wild. At the pressures involved, one suggestion is that fleeting molecular states form inside the electron shells of atoms. They would then decay in a burst of soft X-rays. That idea is highly speculative and has never been confirmed. If it happened, it would change how the impact fireball couples to everything behind it. There's one proposal for getting around all of this, and it's clever. Stop trying to launch a projectile. Instead, use a pulsed laser facility to create a small ball of plasma with the right energy and the right power density. A micron grain deposits its energy in about 1/10 of a picosecond, and modern short-pulse lasers reach that timescale. Put samples of real spacecraft material at measured distances from the event and watch them respond, frame by frame. You don't recreate the impact, you recreate its consequence, and you infer backward. Nobody has proposed a better terrestrial simulation, and it has never been done. So what does the crater actually look like? How deep does the shock reach? Does the debris cloud come back and hit the sail? Does the fireball ionize the electronics sitting behind the impact point? Does any of this behave the way the equations say? Nobody knows. Not one of those questions has an experimental answer, and none of them can get one with the machines we have. Now imagine the paperwork with your name on it. Billions of dollars, decades of work, thousands of spacecraft. And on the line marked verification of the primary failure mode, the honest entry is that no test exists. Would you sign it? That's the sixth place the arithmetic broke, and it's the one that closes the door. For the first time in the history of spaceflight, the failure mode most likely to end the mission cannot be reproduced on Earth. Not by any method anyone knows. So what actually happened to the program? It stopped, quietly and without anyone announcing it. Of the $100 million pledged in 2016, roughly $4.5 million was spent across about 30 contracts. One of the central propulsion groups received around $200,000 over 8 years. That was less than the same group was already getting from ordinary space agency grants. Teams stopped as their funding ran out. A group in Sydney working on sale materials finished their part, heard nothing more, and moved on. By 2025, the program was being described as on hold, with pieces of it transitioning to other people. There was no final statement, nothing closed. It simply went quiet, an odd echo of the thing it was studying. And the money was never the point. $100 million sounds enormous. It's roughly what a mid-sized movie costs. For a technological program of this class, it's a rounding error, and everyone involved knew it. Estimates for building the system run from $5 to $10 billion, and those assume best cases on laser prices and sale manufacturing. The program's own director put it plainly enough. It looks feasible. It probably isn't feasible until later in this century. There's also the problem nobody can engineer around. 100 gigawatts of coherent light, steerable across the sky, is a weapon. The founder said so out loud, and said the only answers were international cooperation and trust. But the science it started did not stop, and this part matters. In January of 2025, a team at Caltech built a light sail 40 microns square out of a silicon nitride membrane 50 nanometers thick. 40 microns is about half the width of a hair. They hung it on tiny springs like a trampoline, put it in a vacuum chamber, and pushed it with a laser. Then they measured the push. In femtonewtons. It's the first direct measurement of radiation pressure on a light sail membrane. The force came out lower than expected. That's exactly the kind of thing to find out on a bench rather than in flight. In 2026, a group in Delft went bigger. Millimeter-wide sails patterned with billions of holes. They reflected 99% of the light that hit them. They held up under laser intensities comparable to the surface of the sun and moved by nearly 2 microns under the beam. That's the state-of-the-art on the propulsion side, and it's real progress, moving every year. The largest sail any laser has ever pushed is a few millimeters across. The mission needs 4 meters. That gap is wide. It's also a gap people can work on, and are, which is why the acceleration turned out to be the easy part. Not easy in itself. Reachable. It can be built, measured, argued over, improved, one bench at a time. The dust can't be reached at all. There's a manufacturing problem hiding in that gap as well. A full-sized sail needs billions of nanoscale holes cut into it. By conventional methods, the patterning alone came out at around 15 years of machine time. New etching work has brought that down. The kind of obstacle nobody thinks about until somebody tries. And that may be the real product of the whole exercise. In 2016, interstellar flight was a fantasy with a price tag on it. A decade later, it's a numbered list of specific, named, published problems, most of them with somebody's calculation underneath. Fantasies don't have failure modes. This one does. The entire experimental history of laser propulsion would fit comfortably on your thumbnail. Let's come back to the grain itself. We've spent the whole night on what it does, and almost none of it on what it is. By mass, roughly 2/3 of interstellar dust is silicate, rock in the ordinary sense. Amorphous magnesium-ion silicate, around 3.5 grams for every cubic centimeter, which is a little denser than window glass. The rest is carbon-bearing material at closer to 2 grams per cubic centimeter, about the density of coal. So much for composition. The structure is stranger and much less certain. The grains are probably not solid pellets at all. The picture that keeps coming back from the evidence is a fractal aggregate. Nanometer-sized pieces stuck loosely together by cold contact over millions of years into a clump full of empty space. Some models put the porosity above 90%, more like a dust bunny than a pebble. And that matters more than it sounds. A fluffy grain hits differently than a solid one of the same mass. It deposits its energy over a longer path into a wider spot with a different shock. Every number in this script assumed a solid. Nobody knows how much that changes the answer. It's on the list of things we can't test. Where the material comes from is settled, and it's the good part of the story. Grains condense in the cooling outflows of dying stars, carbon in the winds of red giants, silicates around older, oxygen-rich stars drifting outward as the star sheds itself. Supernovae make more of it in their cooling debris. Then it gets destroyed. Blast waves shatter grains and sputter them back to atoms. Only a few % of everything the stars make survives out in the open. What's left coagulates again in cold clouds, gets broken again, and goes around. A grain lasts something like 50 to 100 million years between being made and being unmade. Set against the age of the galaxy, that's a few months out of a lifetime of 80 years. The dust out there right now is new. It isn't ancient wreckage. It's the current inventory of a galaxy that is still running. And it carries a record. The record is what keeps drawing people back to it, quite apart from any spacecraft. A grain is a sample of a star that no longer exists. It's a physical piece of stellar chemistry, delivered to us by nothing but drift. The crystals inside the 2 intact grains we recovered shouldn't have survived that cycle. They did, and nobody has explained it. Which is worth remembering about all of this. The dust isn't only an obstacle. It's also the only direct sample of the wider galaxy that ever comes to us on its own. And it's the same material that made everything here. The same silicate that would punch through the sail is the rock under your feet. The same iron that shows up in the recovered grains is in your blood. It's doing what iron does, carrying oxygen around your body while you listen to this. The obstacle isn't foreign matter. It's the feedstock. It's what we're made of, encountered at a speed we were never meant to encounter it at. So here's where we stand. We can build the laser. We can build the sail. It can be brought up to speed in 10 minutes and aimed at the right star. We cannot count the grains. We cannot test the impact. We cannot hold it steady. We cannot carry the shield. We cannot leave the sail out, and we cannot fold it away either. And we would not find out. Not for decades, and maybe not then, because from here, failure and success sent the same signal. And yet, the only reason we know any of this is that we went and looked. Dying stars make grains. Grains make clouds. Clouds make suns and worlds and oceans. Oceans make bodies. Bodies make eyes. And the eyes look up and build instruments and weigh the grains that made them. None of that lightens the sail. It doesn't thicken the shield. It doesn't close the distance between what a laboratory can do and what the journey needs. The arithmetic is still broken in every place we found it broken, and understanding why has not repaired one of them. But there's something worth holding in that. We found the problem before we launched. We found it with instruments and with argument and with people willing to publish a number that ruined their own plan. That is not nothing. That is the whole method working exactly as it should and telling us something we did not want to hear. Thank you for joining me on this journey through the emptiest, cleanest, most ordinary material there is, and through the way it stands between us and the star. If you'd like more nights like this one, subscribe and leave a like before you go. It's the only reason I get to make them. And the next time a shaft of sunlight crosses your room and you see the dust turning over in it, remember what you're looking at. Good night, and may everything around you stay exactly as slow and exactly as harmless as it looks.